Hello, we're going to try a problem that involves the superposition principle uh, that uses potentials. Um, this is a basic example, classic, I might say, of a dipole, okay, positive and a negative charge, and how the summation of these potentials from these two charges affect area around it, okay? So diving right in, I have taken the liberty, again, this just saves time of writing all the given, the goals, and the formulas needed. I would consider the diagram here given. If it's not drawn out for you, I would recommend drawing out the diagram because it helps understand the spatial, or just the spacing between the charges all around. Okay, so at the origin we have a charge of 5 microcoulombs, and just as a reminder, micro means how much? Means 10 to the negative 6. That's what the prefix means. So we'll need to put that in later on. And 3 meters away we have a negative charge, but take note that it's not equal. So this is an unequal dipole. Okay, so this one is less, but it's negative. Okay, and what we're looking for is what is the total potential at this particular point right there, 4 meters above the positive charge straight up from the origin. Okay, and how much work would be required to take the third charge of 4 microcoulombs, we're going to assume it's positive, from infinity all the way there. Okay, there's a reason why we say in electrostatics taking from infinity, because that, you know what, I might get ahead of myself. I'll explain that later. Formulas that we'll simply need is the superposition of potential, that the sum of the total potential at a certain point is just the sum of all the potentials that exist. And here, for the first part, we only have 2. We'll need this formula, and I just realized I'm missing one. Work is equal to, well, this is actually from physics 1. Work's equal to the change in potential energy if this is a conservative force. There we go. Okay, cool. So from here we can go ahead and dive right into the solution, rather. And the first thing we're trying to find is the total potential at point P. Oops. It's simply, honestly, it's just that. That pretty much is it. Okay? And we're using the formula for potential right there. So, whoops, actually I need to spell that out now. Q1 over R1 and I realize now we will need Pythagorean theorem. Can't get away from that, huh? Okay. Now if this distance is 4 and this is straight above, that's right angle, then there's only 2 other choices. This is what we call a Pythagorean triple, and this is 3 right here. You can solve for it if you want, but I can tell you right now that's equal to 5 squared. This is known as a Pythagorean triple. Okay? And as you can see, I can actually move that out. And which one is negative? Okay, there we go. Got it. Q1, R1, they don't have the same R's. R2 is 5. Okay, so I'm going to move it over here and then actually plug out the Coulomb's constant. Don't forget the units. We're going to analyze the units later. Then let's take a look at the charges. Bringing it down. This one is 4, because that's the height just above right there. And then this one is negative, so we do retain, for potentials, we do retain the sign of the charge, unlike electric force where we determine the direction later. Okay? Now just a little analysis on the units. So from here, we're going to get something Coulomb over meter and times that guy, that ratio of units. And you can see something cancels out. Okay? And that's equal, whatever we're left behind with, one of the Coulomb stays there. Oh, what is that? That's actually joule per Coulomb, which is the definition for volts. And sure enough, if it's potential, it should be in terms of units of volts. Okay? And, hold on. Let me spell that out. Apparently what we get here is 1.1. No, wait, no. Let's go ahead and put the final answer. How many significant figures do we have? Okay. Okay, so we end up with 7.60 times 10 to the 3 volts. That's 7,600 volts. Okay, that's pretty high. This is the potential point P, and that is our first answer. Okay, this is A. Okay, now for B, we need the work done and how does that affect the potential. Okay, now I'm going to borrow a formula, which I should probably include here. Let me write it down again here. That the potential is the potential, electric potential energy per unit charge. Multiply both sides by Q. Use this technique in a past video, and I get that the electric potential energy is this Q3. It's delta V. Okay. Now this delta V is actually the difference between moving the potential at point P versus infinity. Now what is this infinity? Let's break that down. Okay, if potential is KE and it's Q3, what's the distance? It said infinity. If this infinity is defined as a very, very large number, then practically this entire thing would be extremely small. It approximates, actually, that should be the symbol for 0. Okay, so this easily becomes the unit that we had before minus 0. Okay, so this is 4.0. Moving the micro again, times the answer we got earlier. Now what unit should we end up with? Running out of space. If I have, breaking down the units. Units are important. Units have feelings too. CV, but volt is defined as joules per coulomb. As you can see, that cancels out, and you're left with units of joules, and that's good because the units for work are indeed in terms of joules. I'm running out of space. I might as well just write it down here. Okay, so the answer, big number, small number rather, it actually turns out that we have less than 1 joule of work is applied. Quite small. Okay? And there we go. So just to recap, this is just an example of seeing how two charges, in this case a dipole, affect the electric potential that is around it. Okay? And remember, electric potential is related to principles of physics 1, that of work and energy. Got it? There we go. Enjoy. Ciao.